Hi everyone, our lesson today is permutation with replacement, repetition or return using this general formula here. So our problem is we have an urn containing 3 balls marked A, B and C. We are asking how many possible outcomes can we have if we withdraw the balls as follows. So first rule, withdrawing the ball in 2 consecutive turns. Second rule, we return the ball to the urn. And third rule, we write the name of the withdrawn balls in order. We have to notice that in this problem we have 3 objects and we have not 3 withdrawals but 2 withdrawals. So this is a different issue than the one we tackled before. Now let's go and see. We have this urn here with the 3 balls. We are withdrawing the first ball randomly. This is the first withdrawal, and writing down the name of this ball, and then we return the ball to the urn and we mix these balls together to guarantee that the withdrawal process is a random process. Again, for the second withdrawal, we withdraw ball C and we write its name down here. We return it back to the urn and we mix the balls again. So we can repeat this process over and over again to generate a sequence like A, C. So this is one withdrawal cycle. We may repeat this cycle few thousand times to generate a sequence like AC, BA, CC, etc. We call a sequence AC, we call it a sample point. Why do we call it a sample point? Because if we get all the possible outcome of this experiment, every sequence like AC can be represented as a point. So as if we have a group of points instead of a group of sequences. This is just a naming we can find in some probability books, and I prefer to call it a random sequence. So now we have an AC. What does it represent? AC, which is a sample point as they call it. A represents the first event, withdrawing ball A, and C represents the second event, withdrawing ball C. Now we are going to define the length of the sequence, which is the number of symbols in the sequence, which is 2 here, or they call it sometimes sample point size. Now we want to know how many possible outcomes we may get if we repeat this experiment or cycles a few thousand times. We can use the cycle generator, and we want to know all possible outcomes of these sequences. So we are going to use the tree diagram for that. So in the first withdrawal we may get A, B or C. And for each possibilities, again, we may get A, B, and C. So we may withdraw B and then A, or withdraw first C and then A, and so on. So this is for the first event and the second event. We are withdrawing in 2 consecutive turns only. So we have 2 events, and the possible outcomes we are going to write down. So we may get AA or AB or AC, and we write all the possible outcomes here. We have to remember that AB is different than BA, so every element here is counted separately, and the reason is order is important. Otherwise, if order is not important, then we are going to count AB and BA only once. So these are all the possible outcomes. We are going to write them here separately, and we can write them using group theory as group S, containing all these possibilities. This group S we may call sample space. Actually, sample space is another name of all possible outcome of the experiment. And if we take one element in the sample space, we are going to call it a sample point. We may also call it a sequence, generated sequence, and we are going to define the sample point size, which is the number of symbols in this element. How many symbols we have? We have 2. So R, which is the sample point size, is equal to 2. Now we are going to compute how many possibilities we have using some mathematical terms. So here is all possibilities. We divide the main tree into subtrees, the first one, the second one, and the third one. Each subtree has 3 elements. We add them together and we get 3 times 3, which is 3 to the power of 2. So what is 3 to the power of 2? It is n to the power of r, where n is the number of objects and r is the length of the sequence. So if the sequence has 2 symbols, then r is equal to 2. Now we are going to write that in a concise form, which is PRNR, which means the following: permutation, which implies order. So now we have permutation with replacement, or with repetition, or with return for n objects taken r at a time, where r is the sample point size or sequence length. So we read this as follows: permutation with replacement of n different ordered event or objects taken r at a time. Now we may find different notation in other books like PNR, but we are going to add r here to emphasize that there is a replacement in this law. So we know how to use it and we remember it very well. Now what is n? Number of objects in the set, and r is the sample size or length of generated sequence, as we have seen before. And now we need to know the conditions according to which we can apply this formula. We have 3 conditions: order, replacement, and r may be 1 or 2 or 3 or n or number bigger than n. So r is a natural number starting from 1 and going to infinity. So is it really possible for r to be bigger than n? Or in other words, is it possible for the generated sequence to have bigger length than the number of objects generating this sequence? Let's have a look at this tree diagram. We are going to withdraw here the walls in 4 consecutive turns. So we have now 4 events, which is bigger than the number of objects we have, which is A, B, and C. So for the first event, we may have A, B, and C. For the second event, we may have for each possibility another A, B, and C. And that's the second event. For the third event, we have the same. And for the fourth event, we generate all these sequences. And now we write them all down. And now we are going to compute the numbers of these generated sequences by dividing this tree into subtrees. Now each tree contains 3 times 3 times 3. Now we add them together, 3 to the power of 4. So n is the number of objects, which is 3, and r is the sequence length, which is 4. So yes, this formula can be applicable if r is bigger than n, and this is very useful for many permutation issues we are going to face later. So we may have a close look at every subtree. So every subtree has 3 times 3 element times 3 subtrees, so we have 3 times 3 times 3. and this is second subtree, and this is the third subtree. So now going back to the old issue, we are withdrawing from an urn containing 3 balls in 2 consecutive turns, and we return the ball each time, and we do that in order. So these are all the possible sequences, and this is the number of all possible withdrawn. If we repeat this experiment a few thousand times, and we can apply the formula, a previous formula, to get the number of possibilities or the sample space size. So to solve this problem in general, we have to define the event. First event is withdrawing the first ball, second event withdrawing the second ball, and then we can write this down this table indicating the events we have, the first and the second, and the way according to which this event may occur. So we have 3 ways for the first event and 3 ways for the second event, and all possibilities are 3 times 3. We can apply this formula knowing that n is the number of objects in the set, which is 3, and r is the sequence length or size of point sample, which is 2. And we apply this formula and we get the number of all possibilities to generate a sequence according to the previous rules. Or we can do that in more abstract way, writing first cell and second cell, and in each cell we fill the number of ways this event may occur, and we compute all the outcomes. Now at the end, we have to remember that to apply this formula, we need these 3 conditions: order, replacement, and r is a natural number starting from 1 to infinity. Thank you very much for listening, and we are going to see in more examples how to apply this formula.